And this is our agenda for today. We'll be starting with a welcome, and then the overview of the PhD program and curriculum. We'll have 2 lightning talks for data science field, and then an overview of the medical school track. Then the medical school track lightning talks, some admissions and application reminders, and then ending with a final Q&A session. But attendees are free to submit Q&As into the Q&A module, and you can also review the answers and upvote any of the questions in the Q&A. So thank you for joining us today. We're starting off with a welcome and overview of the program and curriculum by Professor Cristina Savin, Director of Graduate Studies of the PhD program and Associate Professor of Neuroscience and Data Science at NYU.
Hello, welcome. We're very happy to have you here. So as Tina was mentioning, I'm currently the Director of Graduate Studies, and I want to give you a little bit of an idea about what CDS is about and what our CDS PhD program is about. So next. So the easiest thing to start is to ask ourselves what exactly is data science. And the way we think about it is really as the discipline that lives at the intersection between machine learning, or what these days we call AI, which is methods and algorithms for making sense of large segments of data, and application domains. And here we're listing a bunch of different applications that are relevant for our CDS faculty. So data science happens at the intersection of these two. Check next. And it's really about the interesting science that happens by putting these things together. Now, traditionally, these different disciplines live in different departments. So you're going to see the methods part in typically CS, math kind of departments. And then the application domains will have their own university department most of the time. But CDS was one of the first to recognize the importance of bringing these different people together under the same roof in order to facilitate this interdisciplinary interaction between the two. And the CDS PhD program is a continuation of that idea. So we're trying to train the next generation of scientists that can work at this intersection. Next. So a little bit about sort of like the logistics, or sort of like the structure. Within the program, we have subdisciplines that cover all of these bases. So you can work with faculty that focus on core machine learning questions, developing new algorithms. And there's a range of different science and application domains that were listed in the previous slide, or you can do like pure theory, or more engineering on the data science kind of databases, visualization. So we're kind of spanning the entire life cycle of data in this context. The other thing that I would like to highlight is our program in responsible data science. We're sort of like at the stage where there have been amazing technological developments in this domain, and we have to like start thinking critically about how these impact our day-to-day life. That's quite important. And again, one application domain that CDS has been spearheading. Finally, as Tina mentioned, we have an entire medical school track that is in collaboration with the medical school at NYU. And there, the goal is to take machine learning into the domain of healthcare in different subdisciplines. So you're going to hear a little bit more about the science behind some of these ideas in the lightning talks. But next, I can tell you a little bit about about the curriculum. So it's a 72 credits total coursework, which kind of you can think about as being distributed between 3 kind of things. So there's a set of core courses that make sure that you have strong foundations in data science that are common within the cohort among the PhD students. Then there's a number of credits that go directly towards your research that you're doing in the context of with your primary advisor or potentially with collaborators. And finally, there's a range of electives that allow you to like hone in on the particular subdomain of data science that's the topic of your PhD. We try to monitor progress and give feedback regularly via a yearly review. And sort of like there are a couple of important milestones like the comprehensive exam and the depth qualifying exam that make sure that you've achieved the level of performance required to proceed towards graduation. Finally, we encourage our students to teach because we think that's a good idea, not only because sort of like we need TAs, but because it's an opportunity for you to learn how to communicate your science and your sort of like your knowledge to people that are maybe like less informed and sort of like skills that you would need to take with you in whatever you end up doing after graduation. Next. So that's it for now. We're going to have an opportunity to ask questions about the general structure of the curriculum and how the program works after the lightning talks. But for now, we're going to hear a little bit from people in CDS about their science.
Thank you, Cristina. Let's see, Cristina, I'm just going to quickly review the Q&As to see if there's any questions that might be appropriate for you to answer. Someone asked if the lecturers have retired, can they use their graduate colleagues who are now lecturers to write the recommendations?
I mean, you should get letters from people who know you well. I don't know that this is a specific scenario that we have in mind. If whoever writes the letter can write something sensible and like they know you enough to write a good letter, then sure, why not?
Someone asked, are there particular attributes or experiences that the admissions committee is looking for in the statement of purpose? Yeah.
So it's complicated, but sort of like I would say that curiosity and sort of like interest in actually doing science, so a problem-driven or a question-driven approach is something that I particularly find appealing in a statement of purpose. But different people might have like different takes on this. So like don't take my view as the thing that you're necessarily supposed to be doing. We want people that are technically competent, that are excited about doing science, and whose interests align with the faculty in CDS, I would say. So those are definitely important criteria.
Got it. Let's see. Someone asked if it's better to put 1 or 3 preferences for research topics. Our application lets you choose the different research areas. You get a primary choice and then also a secondary choice, and it's the research areas that we provide. So it's a checkbox question on the application.
Yeah, but again, like actually tick only the boxes that you think reflect your interests of what kind of science you would actually want to do. Don't think that it's a better idea to just like include 5 different elements and say like I'm interested in everything. That doesn't tell us much about who you are, and it's sort of like if anything it might confuse matters. So
someone asked, what's the difference between data science and data analytics?
okay, so I would say sort of like data analytics is maybe there's a terminological thing that people kind of in different subdomains might call the same thing differently. But there's also sort of like I would say that data science is a bigger umbrella that like covers all of these additional aspects of data processing, the application to specific domains that I would not consider a part of data analytics. Yeah, so it's it's a subset. Data analytics is a subset of what I would consider data science.
There's a few questions about whether, I guess, publishing papers in international conferences or journals matter for applicants.
Some research experience is definitely a piece of evidence for us that you're ready and interested in doing research, and sort of like publications are a tangible proof of that. So in some sense, they do matter, but it's one piece of a puzzle, so that in itself does not guarantee an interview or admissions.
Someone's asking if the program is specifically looking for some students of certain backgrounds, if they can have more information about that.
So we definitely want people with strong quantitative skills, because sort of like that's kind of a prerequisite to be able to do the work. And exactly which students will get recruited in a given year might be a reflection of who of the current faculty are looking for students in that year. But beyond that, I don't know that I can say anything specific.
Someone asked if they should contact a faculty before or during the application process.
Yes, but be mindful of people's time. So again, like if you have like one particular faculty whose work you're excited about and you would only consider working with them, then you probably want to reach out and make sure that they're recruiting students this year or something like that. But like sending a generic email to all faculty on the list is not going to be a productive use of anybody's time.
Someone generally asks, can we still apply if we do not have a specific research topic in mind, but a general area?
General area is fine. It's just like it can't be the entire data science general area. So some narrowing of field might be helpful.
This is the last question for you, Cristina, since Guy will be going next. Is the program solely focused on the medical field, or what other industry fields are available in the program for research?
So definitely not. So the medical track is one particular sub area that we're like representing in the context of today's discussion, but there are all of the other application domains that we saw in the first slide are represented. So personally, I work in neuroscience, so machine learning applied to neuroscience, how the brain works kind of questions. We have people in cognitive science, we have people in social science, physics, whatnot. So if you go to our webpage, you're going to see the entire list of faculty that there are in the science applications niche, and you can get the sense of what the entire set of options is. Music, urban planning, there are quite a few.
Thank you, Cristina. So yes, please continue putting your questions in the Q&A. We'll, as you can see, my colleagues Joshua and Francesca has been answering them. But now we're going to head on to the lightning talks. And the first lightning talk we have is by a current PhD student, Guy Davidson, who is advised by Professors Brendan Lake and Todd. Yes, and Guy, I'll let you share screen right now.
Right. Can someone confirm that you can all see my screen?
Yes, we can.
Awesome. So in the next 5 to 7 minutes, I'm going to try to give you a brief rundown on the intellectual journey I went through during my time at NYU. I'm a PhD student. I'm in my last year. As Tina mentioned, I'm working with Brendan Lake and Todd Gorekis. Both of them are professors in the data science program, but it's also collaborative work with some other folks at NYU, Julian Tegelius and Graham Todd from the Tandon School of Engineering. And that's one of the neat things about NYU. There's a lot of really great people to collaborate with who are also outside of your department. And so if we flash back to like me being a first-year PhD student somewhere in the winter of 2020, this is the before COVID times, the world is very different. I was reading a little bit about how people think about exploration in reinforcement learning problems for artificial agents. And very often, there are sort of like a number of approaches, right? Like some approaches are based on randomness, right? Like you can imagine doing something like either acting greedily based on the best action or randomly sampling a new action to try. Other approaches call on curiosity or intrinsic motivation, but like that often felt dissatisfying to me because it's basically like, do I know what will happen if I take this action? Then I started reading about goal-based exploration methods. And very often people either formulate a goal for an agent as like a state, like get to this point, or maybe an image of the world to try to achieve. And that's where my like cognitive science self started thinking, there's something interesting here. What do we know about how people come up with goals and how do we represent goals? And just as a cute example, here are a couple of pictures of Logan, my advisor's son, coming up with new and interesting goals like building a truck carrier truck that I've never seen anyone build before. But it's really hard for me to think about how do I come up with a state that is a truck carrier truck. Or if I didn't know to have that concept, it would be really hard for me to generate an image of this. And it's not just kids that can do this. So in a move that might date me, this is a commercial from the 90s where Michael Jordan and Larry Bird were playing a game of horse. And they came up with like weird shots to make, like from one knee, or they're going to sit in the rafters and try to make a shot that's going to bounce under one and over the other one. And the thing I became interested in is studying how these goals come up and like how do we generate them. And to be a little bit more specific, the type of things that we were going to study are building on work that sets at play as a like creative and compositional goal setting and solving. And concretely, we did 3 things that I'm going to tell you about very, very briefly. We proposed a framework that thinks about goals as a type of program. We studied these empirically by collecting data from people in a naturalistic experiment. And of course, we built computational models that can generate human-like goals. So what does that look like? And what are the sort of things that I ended up trying to think about? So one thing is this idea of how can we represent a goal as a type of program? And maybe if we think about something that's often used in robotics, like pick the red cube and place it on the blue cube, maybe the program would be to sort of like put on the blue cube, red cube. If we think about a goal like the players were coming up with in this game, it might look something like, well, I want you to throw it over the second rafter and make it off the floor and nothing but net. And so it might look like this following sequence of things where you want to see the basketball thrown, and then you want it to be above one rafter, and then you want it to touch the floor, and then you want it to be in the basket. We can think about representing the truck carrier truck as, count how many trucks you managed to put on the carrier truck. Or we can think about a block stacking game, like one Logan played younger in another video that I skipped today, as, also counting this. And like, why do I think this is interesting? Why is this something that I find compelling? These programs give us a couple of things. And one thing is like a very clear definition of semantics, right? Like if I tell you a sentence like over the second rafter, off the floor, nothing but net, maybe you're like, what are you talking about? What does that mean? But if I show you this program and you spend a couple of minutes reading it, you can be like, okay, like you very clearly want these things to happen in a row. And so there's a like very clear definition of the goal that an agent can then use to plan and to try to pursue it. And now that I've told you about like this sort of like the conclusion of this idea, how did we get there? What did I do over the last couple of years to develop it? And the first thing I did is I built an experiment platform where I collected games from people that they described in natural language in this like 3-dimensional environment. And so people came in and they played in this room for a while, and then they described a game that they could play, which is a type of playful goal. Once I had a data set of these, I started thinking about, well, how do I model this as a computational problem? And so you can imagine that the thing I have is I have a collection of programs that people created. And some of these are real games that people created in the experiment, like throw the ball so it hits the wall, then bounces back to you. or place the bin on the bed and the dog bed next to it, and then throw dodgeballs into either of them. And what I want to do is I want to learn how to generate new programs. I want to like find, okay, so these are good, like they have high fitness because people came up with them. And I want my model to be able to come up with games such as like, you have 30 seconds to throw dodgeballs to land on the top shelf. And that is a real program our model came up with. Or place the bin near the rug and throw balls at it. And these are kind of similar to each other. But ideally, I'd also get my model to do things that are more interesting, like come up with weirder games or goals, like place the bin on the rug and throw basketballs onto it and put chairs on the desk, which is like, okay, I can do this, but I don't know necessarily like why I would do that. And some of the reason why that's hard is because it's also really easy to generate programs that are kind of weird, like put the desk in a chair. What does that mean? That doesn't mean anything, but it's a valid program. I'll tell you very briefly as to how we solve this. We have two steps. One is we try to learn an objective function where we translate programs from natural language to this sort of program representation. We corrupt some of them, and we try to learn a function that will give a high score to real games that people created and a low score to these corruptions. To generate new programs, we sample games from a collection, we mutate them a little bit, and then we reinsert if it's novel or if it's more fit. I'm not going to tell you about everything I tried to do to study this, but if you are curious, you can find a paper on my Google Scholar or website. But we then needed to work on translating back from these programs to natural language. Because this is an interesting and hard generative problem, we need to think about how we have people evaluate it. We needed to analyze these human evaluations to really study and get a sense of like, does our model do what we think it does? And we needed to run some ablations to verify that our model components that we built are actually necessary. I will skip talking about follow-ups, but I'm happy to answer questions if people are interested. But I will say that like this, I think my intellectual journey at CDS was like unique, but also every candidate's journey here is unique. We have people who work on neuroscience and psychology and core machine learning and language processing and vision and pretty much anything under the sun that you can imagine doing with data science. I feel that I was really lucky because I could work with, two advisors who are both interested in and affiliated with data science, but are also in the psychology department. And so I could learn from expertise in both of these. I could also collaborate with other people at NYU, including starting new collaboration that neither of my advisors have worked with these folks before. And yeah, I've been having a great time. I'm about to graduate this year and, happy to answer any questions.
Thank you, Guy. Let me see if there are any questions specific for you. Guy, I don't know if you can talk about this, but there are a lot of, not specific to your presentation, but there are a lot of questions from prospective applicants about reaching out to faculty during the application process. So what was your experience like, or what would you recommend to these prospective applicants?
Yeah, I can talk about that. First thing, go on the faculty's website. Some professors are like, yes, please reach out to me. Other professors are like, please don't reach out to me. If a professor is please don't reach out to me, you should have a really, really good reason to not do what they're asking. Next, if you are going to reach out to someone, make it specific. I reached out to a lot of people before I applied, and when I reached out to people, I would always refer to a paper they wrote or like something that I know they are working on. If you send a generic email, and I've reached a point in the PhD where I also get some of these, there's no reason for me to answer you if I like, oh, you're curious about work in machine learning. Great. That applies to like some, hundreds of professors at NYU. If you want a faculty member to actually find your pitch compelling, you should show them that you are actually specifically reaching out to work with them and you're excited about them. And then I'd say the last note is like, make these emails short. Professors get a ton of emails. The email should be very clear. Should be like, hi, I am this and that. I'm applying to grad school. I would love to work with you. Here's why I think I might be interesting. Here's what you do that I might want to work on with you. And like, here's maybe a quick question. Like it should not be more than these 3 paragraphs. Each of these 3 paragraphs should be pretty short. It should be abundantly obvious to the professor why you're emailing them. I think also, Tina, I saw a question earlier that was about like some professors are affiliated with multiple programs. Where should I apply? In general, NYU only allows you to apply to one of these programs at a year. For example, when I was thinking about applying to work with Brendan, I was like, do I apply for data science or do I apply for psychology? And I thought that my interest in my prior work that was more computational would make me a better candidate in data science. And that if, suppose I knew I wanted to work with Brendan, and I'm still working with Brendan and I'm very happy, but like, suppose that didn't work out and I had to go find someone else to work with, I felt that it was more likely that I would find somebody I'm excited to work with in data science rather than in psychology. But think about like where you would fit as a candidate and where there are other people you might be excited about working with.
Thank you, Guy. To add on to that, our PhD admissions webpage on Center for Data Science website has the PhD advisory group on the bottom of the page, and those are the faculty who potentially can take students. Not all affiliated CDS faculty can solely advise a student within CDS. So if you're interested in an affiliate faculty that's not listed as part of the advisory group, then you might want to look into their personal faculty pages to see which departments they advise students in and if they are accepting students for this year.
And that, by the way, that's another good thing to ask if you're going to email a professor. Some professors will list on their website, hey, like I'm planning to take students this year. Hey, I'm not. But like ask them, because if you know that somebody's not planning to take on any students, then applying to work with them just means that, you're not going to get in. I saw there was some other questions. Did I apply to work with Todd and Brendan specifically? I mean, I knew that I wanted to work with them. And I think that when you think about where you apply to a PhD, like apply to CDS if there are people at CDS you would be excited about working with. If you look at the list of faculty and you're like, there is nobody here that I really want to spend 5 to 7 years of my life working with, then like maybe you should apply somewhere else, and that's okay. There are many great faculty here, and I think that if you're here, you probably already know that. But really consider like, these are the people, I really want to work with Cristina. I really want to work with Kengan Cho. I really want to work with Brendan Lake, etc. And I think that's really, really important.
Thank you, Guy. I guess one last question, since a lot of students have been asking about this. Someone wants to know how many papers did you publish before applying to NYU? Did you apply right after your bachelor's?
I applied right after my bachelor's, but I also started my bachelor's when I was 25. So I don't think I am exactly a standard candidate for this type of thing. And I had maybe a couple of like short conference, like not, full on 8-page conference, like reviewed papers, but like 4-page, like conference extended abstracts, and a paper that was like under review at the time, but I had no publications. However, also this was like 6 years ago, and the world is a vastly different place now. And like, maybe the sense I can tell you that from hearing how Brendan and Todd talk about prospective applicants is, it's not that you have to have publications, but it is that you have to know what research is. And one really easy way to show that you know what you're stepping into and like what it actually means to come to a PhD and do research for 5, 6, 4, 7 years is that you have done research in the past. And the best way to show that you have done research in the past is to have publications. And so, like, if you don't have publications, think about other ways to showcase that you know what doing research means and that you can, like, make that a compelling thing that like, oh yeah, they know what they're stepping into. They're not just going to come in blind into this thing.
Thank you, Guy. Thank you very much for your presentation and answering the Q&As. Our next lightning talk is Professor Eunsol Choi, Assistant Professor in Computer Science, which is part of the Courant Institute at NYU, and Data Science. Eunsol, I'm going to stop sharing so you can share. Let me know if you have any concerns.
Sure. Can you see the screens?
Yes.
Okay. I will get started. Okay, so I'll start with a brief introduction of myself. As Tina introduced, I'm assistant professor in CDS and Courant computer science, and actually this is my very first semester at NYU. Before that, I was at UT Austin as an assistant professor, and then spent a little bit of time as a researcher at Google Research and did PhD at University of Washington. And my lab studies natural language processing and machine learning. And at the moment, there are 7 students, 1 master's student, and 2 and 3 undergrads who are working on various aspects that I'm going to talk about in the next 5 to 10 minutes. So largely, my group is really interested in helping humans to access knowledge. And a lot of knowledge that humans have acquired is written in text. So we do text processing to help humans to untap access to this large-scale knowledge. It has a lot of different applications, like help medical professionals to diagnose their patients, or help journalists to process large volume of documents. And our goal is to build an automatic system that can help this. And we use language as an interface between the humans and this knowledge. So humans ask a question, and we're trying to provide an answer in natural language form. Yeah, so that's kind of larger research goal of our lab, build systems that can interact with users to find information and reason about it. And this involves a lot of different pieces. So I'm going to walk through a couple of things that we've been working on recently. So one thing is like, where are the knowledge coming from? These days, we are training like really, really large scale language models that's trained on billions of tokens and trillions of tokens, actually. And during the training process, it's trained to predict the next word. And if you can see in this example, if you're trying to predict the next word here, in this process, you're kind of acquiring the knowledge that Paris is the capital of France. And such knowledge is encoded into the parameters of the language models. And this basically becomes one source of information that we are going to use to provide information to the users. A lot of LLMs out there, I'm sure many of you have interacted with ChatGPT. They have like this kind of parametric knowledge that it has acquired during large-scale pre-training. There's another source of information where you can retrieve the documents at test time. So once you get the user's query, you can kind of search the document corpus with Google search and so forth. And then you are going to also use these documents to answer the query. So the thing that we've been looking into is called retrieval augmented language model, which is pretty simple paradigm. So instead of feeding the question into LLM directly, which sometimes LLM doesn't have enough information about it. So we are going to retrieve documents that's relevant to this query, and then simply concatenate the documents to the query, and then the LLM will be able to answer the question more accurately. So this is kind of stuff that we've been working on. In the past couple of years, we've been looking into how can you improve this retrieval augmented language models. We proposed like this small modular very efficient modules to this process. One thing that we introduced decomposer that can look into various aspects of the input query so that the retriever can retrieve a more comprehensive set of documents. Another thing that we looked into is introducing this another module that sits between the retrieval and LLM, which we called compressor. That basically looks at a lot of noise information output from the retriever and filter them carefully so that you can pass in only useful information and not distracting information to the LLM. Yeah. And then we also work on how can we improve the LLMs themselves as well. So we were looking into this like kind of, if you do this retrieval augmentations, sometimes you would like to prepend a really large amount of text, and that makes the process very inefficient. So in this work, we are looking into how can make this more efficient by alternating more expensive operations and then more approximate cheaper operations. Yeah. Yeah, so that I've been talking a little bit about the information source, which is coming from the inference time document and how we incorporate that into this knowledge systems. Another thing that we look a little bit is the knowledge in the LLM themselves. And this is really interesting because like LLM, we train it once, which is very expensive process. But then, the world moves on, new documents, new papers, everything comes up. So how can we inject the new information to the LLM after it's been trained? So it's kind of continual learning of the models. And we've been looking a little bit into it. So in this work, we're looking into how can we teach the model to basically hallucinate the relevant information at test time, even when it's not given. So we introduced a simple distillation loss for this, and this was working pretty well. But knowledge editing and continual learning is still a pretty hard problem in many ways. Lastly, another thing that I'm really excited these days is typically when you are working on these knowledge systems, before we aimed for kind of single shot interaction. So user ask a question and then the model either provide an answer and or abstain from answering. And we would like to have more multi-turn natural interactions where, say this person was interested in women's tennis results, not the male tennis results, and then the model gave male tennis winners results, and then user is like, oh, that's not the answer that I was looking for, and then model can ask clarifying questions, which US Open are you referring to, and then provide clarifications, and then get to correct answers and so forth. So these days you interact with this model and they give like wall of text, which is really large amount of information a lot of times, and we kind of are interested in building more multi-turn interaction with these models, basically allowing LLMs to be able to take initiatives and then also learn from interaction with the users after the model is deployed. There's a lot of interesting research questions here. I think that's all content that I wanted to cover today. We've been looking into, as I said, retrieval augmented language models, continual learning and knowledge editing, human LLM interactions, long-form question answering. This means where the answers are pretty lengthy, and then we are trying to understand the discourse structures and how can we better structure those answers. And I also work a little bit on spoken language processing and processing the sounds and synthesized speech with more style tags and stuff like that as well. Yeah, I think that's mostly the time that I had. I would like to thank my sponsors and my students, and yeah, I'd be happy to take questions.
Thank you. And so there were some questions about at the bottom for you. Let's see. Someone asked, I am presently working on ways to integrate nature-inspired algorithms like the genetic algorithms with LLMs for an optimized performance. Is that an area you will like to supervise a student in? I think generally students were, prospective applicants were asking if you were accepting students this year and what areas.
Yeah, I am definitely accepting students this year. Genetically inspired algorithm. I don't know. I think I'm pretty open-minded about exploring a little bit new areas. So yeah, if it looks convincing and interesting, I'd be interested in looking. But I think it's gonna be still somewhat related to the stuff that I presented, LLMs and these stuff. Yeah.
And prospective applicants are wondering if they should reach out to you via email during the application process, or do you want applicants to reach out to you directly?
Yeah, I don't typically respond to applicants' cold emails these days. But like I will definitely look at every application who mentions my name and then will reach out if I'm interested.
Got it. And there were some questions about this, but in the online application, when you're selecting your areas, if a faculty is within that area, there is a checkbox for you to check off all of the faculty that you're interested in. And that's what faculty means when they say that you should indicate your interest in them within the application.
I actually don't know the application process that well as a new faculty, but I think you should check the box that the faculty belongs to, and I think it typically also helps if you mention their name in your statement of purpose.
Mhm. Yes. Yeah, someone asked, related to your presentation, so context distillation is technically a model hallucination rather than model editing techniques.
Yeah, I think the definition of what is model hallucination and what is model editing technique is like not super clear. Yeah, I wouldn't call it hallucination. Even it's still editing the parameters such that the parameters will have more information, but it's about how the information is getting invoked, which is a little bit more similar to. So basically, like you don't call it hallucination if the information is accurate, typically, right? So even though it answers without seeing something, so yeah.
Another presentation related question is, doesn't training LLMs with information from ChatGPT make the model biased, since we are trying to replicate real life instances, not LLM instances?
Yeah, definitely there are concerns with training these models with data that's generated out from the model outputs. I think we are still pretty early stage of studying these kind of questions, and there are pros and cons. I think it's pretty well known that these model-generated outputs are less useful than human-generated output, but it also depending on the quality of the human-generated output because there are a lot of junks in the internet as well.
Someone asked, how can retrieval augmented language models enhance the performance of a custom chatbot? And what benefits do they offer over traditional response generation techniques?
Yeah, I think one major benefit of retrieval augmented setting is that you have some private data that you don't want to upload to train the LLMs, or you have some data that, text that you just wrote yesterday or some information that you got yesterday. Then retrieval augmentation can kind of help you to keep your data more private, and then retrieve from more up-to-date sources without having to update the model.
A student asked about co-advising. As you can see from Guy's presentations, and that Guy is being co-advised by several faculty. That's not uncommon. But Eunsol, from your perspective, what do you think about co-advising if a student's interests cross multiple fields?
Yeah, personally, I was co-advised during my PhD. I had 2 advisors, and then out of 7 PhD students, 3 of my students are getting co-advised. So I'm pretty open to co-advising, especially if different PI can bring something unique expertise to the progress of the student study. I think if you're interested in a certain faculty, it's probably useful to look at their website. I think different professor has different attitude towards co-advising. So if that professor has never co-advised before in the being professor being 20 years so far, it's unlikely that person would suddenly change your mind. But if the professor, you looked at their website and they have a lot of co-advising students, then they are much more likely to be open about co-advising.
Someone asks, can we use RL to train GPT model so that it learns on the fly for all the users, not just for that user?
Yeah, I think using RL, there are people who are research. That's an active research areas. Yeah.
How can LLMs be adapted for low resource languages or dialects that have limited training data? What research is being done in this area and how can students contribute?
Yeah, so I myself work a little bit on the low resource language as well. There are multiple angles. In low resource, there are typically not enough data for evaluations and stuff as well. So developing data is like one avenue that you can contribute. The other is that generating synthetic data with existing small amount of data, and then that can help the model. And the other is like studying some sorts of transfer from knowledge transfer from a high resource language to low resource language.
Thank you. And so I think that's all the questions we'll take for you at this time. Thank you very much for joining us this morning. And let me share my screen to introduce our next speaker. Okay. So we're moving into the medical school track overview section of this info session, and today we have joining us Professor Samit Chopra, who is Associate Professor at Courant Institute of Mathematical Sciences and Department of Radiology at NYU Langone Health. He's also Director of Machine Learning Research at the Department of Radiology at NYU Langone Health and an affiliated faculty with us, Center for Data Science. Samit, I am stopping share so you can share your screen. Thank you.
Thanks, Tina. Start. Can you all see my screen?
I see it. It's not on slideshow yet.
Is it
Okay,
on
great.
Is that now? Okay, cool.
Yes.
Thanks, Tina, for the introduction. I won't repeat it again as to who am I. So, but I will definitely say one thing, that these slides are entirely Dr. Daniel Sordixon's work. He typically delivers this short pitch for incoming students, but for some reason he was not able to make it this year. So yeah, so essentially the goal of this next 15, 20, 10 minutes odd chat is basically to give you a very high level overview of why, if you want to pursue a PhD at the intersection of data science, AI, and healthcare, why you should join NYU, specifically the CDS program, and one of the primary reasons why you should join, other than all the good things that go in the School of Medicine, is that there's a very close collaboration between CDS and the School of Medicine, and especially if you're doing an interdisciplinary research, this close collaboration is extremely, extremely important. And I'll share my views why that is the case. More generally, a very high-level overview of School of Medicine. As some of you might already know, that the School of Medicine is actually one of the leaders in healthcare, not just in the United States, but arguably in the world. And this leadership is not just limited to essentially our advancements in sort of clinical processes or medicines per se, but it's also sort of extends to developing and using modern day technologies to improve and advance clinical care and healthcare. AI specifically is one such area where we are actively focused on more recently, and making good strides in that direction. So we of course strive to become leaders in this field, which is basically at the intersection of AI and healthcare, and are always looking for folks who are truly passionate about becoming of making a difference in this interdisciplinary field and making a real difference to improve people's lives, right? And I personally, my background is not in healthcare, it's in AI actually. I was actually a graduate student of NYU. I graduated in 2008. After that, I was a research scientist in AT&T Bell Labs, then at Facebook AI Research. And until about, I would say 7, 8 years ago, I left Facebook to actually start my own startup, which was at the intersection of AI and healthcare. And since then, I've been involved mostly in AI and healthcare, and have been extremely passionate about sort of doing some interesting work in this direction and making a difference. So I basically have, I would say, 6 words to tell you as to why you should join the School of Medicine. So what are those 6 words? The first one is problems, right? And by problems, I don't mean that the School of Medicine is riddled with problems. I mean problems in a good way. basically what I mean by the term problems is I essentially am referring to the unsolved problems and the unmet need in biomedicine. So School of Medicine is quite vast. It consists of many departments, and it's a significantly huge institution spanning not just the Manhattan borough of the city of New York, but also neighboring boroughs and even Long Island, right? And it has quite many centers, and it caters to a diverse set of set of population, and that's only from a clinical standpoint. From a research standpoint as well, there's many areas of research that School of Medicine indulges in, starting from medical imaging to oncology to genetics, which you'll hear about later in this after my talk, to ophthalmology, to histopathology and stuff like that, right? And with these many areas or many directions of research, obviously very interesting problems prop up, right? Like things like how to preserve brain function with aging, or how to predict and prevent cancers and arthritis and heart disease reliably at an early stage, or how to detect subtle changes in an individual's state of health even before they can be visualized by a human radiologist by looking at their images, or how to build the next level of imaging, for example, that is accessible to all, especially to those who do not currently have access to excellent healthcare. Or in other words, more generally from an AI perspective, the kind of problems we are interested and have a significant amount of focus on is not just about taking off-the-shelf AI models and applying them to healthcare data sets, but more like answering the question as to how can one use AI to sort of generate or ask questions that humans have not currently asked, right? For example, and I'll give you a few examples later as to what exactly do I mean by that. But I guess the bottom line here is there's no dearth of problems as far as the School of Medicine is concerned, where you would want to be that'll sort of gauge your interest, so to speak. And why I'm stressing so much on the problems is because like a problem-rich environment actually fosters innovation, right? Like a prime example is Bell Labs. I'm not saying that School of Medicine is equivalent to Bell Labs in any shape or form. I mean, I guess maybe in medicine you could argue we are, but generally, when people talk about Bell Labs, right? Like, I mean, what we think about are the fundamental technologies that we see right now everywhere throughout in our environment, like the transistors, like the lasers, like the satellite communications, etc., the telephone system. All of these were actually developed inside Bell Labs. And actually, this is a really great book, which if you're interested, you should read if you haven't. And the key things that come out after you read this book is that the reason why such excellent innovations happened within the labs is not just, I guess, people was one key force to lead to those innovations. But the second thing is the sort of the environment of the problems. Like there were no dearth of problems within this environment that people could focus on, and scientists immersed themselves into these problems that excited them and sort of ran away with them. And many things came out from different parts of the Bell Labs, which currently, as we all know, we experience on a day-to-day basis, but not necessarily are fully aware of it. So that's one word, the first word, problems. The second is partnership. Of course, like being in an isolation, I do not believe excellent research can happen if you're sort of in an isolated environment. You do need partners, right? And this is where sorry, by partners, I mean people. This is where a School of Medicine again excels in quite a bit, and we have a whole bunch of smart people, as I mentioned, in various departments across the board, right from medical imaging to oncology to genetics to EHR and stuff like that. And researchers here are basically have a real hunger for data science to work within the School of Medicine, and we have a rich ecosystem within the of departments and centers that work around problems in data science. And if you join as a PhD student in the medical track of CDS, you will be paired up with an advisor on the School of Medicine side and a co-advisor on the CDS side. So, and typically the advisor on the medical side is somebody who is either a clinician who is working in AI related stuff, or sort of a research scientist a research faculty who's had a significant experience in clinical settings, or in essentially advancing medicine. So as a PhD student, you'll be getting sort of feedback or input from both the technical side, which is basically the CDS, and also from the clinical side, which is on the School of Medicine. And that to me is a very key ingredient for success to become a successful researcher in this space. Right. The third thing are the partnerships, where basically, like as I said, like you can't do your sort of research in isolation, and this is again an area where the School of Medicine has excelled in quite a bit, right? Like of course, like there are these internal partnerships where the School of Medicine partners with CDS, they partner with Courant, and they partner with the Tandon School of Engineering. But there are also plenty of sort of external partnership that School of Medicine has indulged in, which has essentially led to a significant advancement in sort of pushing the boundaries of technology and medicine. Right. Specifically for like the two I'd like to quote from a Department of Radiology standpoint are our partnership with Siemens and Philips that allow us to do research in ways that most people or most of our competitors right now cannot do, right? Like to give you a specific example, like our special partnership with Siemens allows us to essentially probe into the internals or the guts of an MR scanner, which is like a closed box medical imaging device that essentially measures some signals, some electromagnetic signals within a human body, and essentially creates an image out of it. And that images get sort of read by radiologists, right? And this whole system is actually quite a black box. So people have their proprietary algorithms, like different manufacturers have their proprietary algorithms as to like how the signal gets acquired and gets translated into an image. And in the end, most people, what they see is an actual image. But of course, that signal is very rich, right? I mean, the kind of questions we want to ask is, are there any additional information within that signal that that we can leverage, or that we can use AI models to leverage, that can improve the diagnostics, right? And if you're a sort of a regular school who does not necessarily have such partnerships as we have with Siemens, you cannot really tamper with the MR machines to get access to that raw signal behind the scenes. And primary reason is because these machines are FDA approved devices, and like if you tamper them even ever so slightly, the whole FDA approval seal gets nullified. Or in other words, you cannot then use that machine like a $5 million machine on clinically to acquire images in a clinical setting, right? And that is a huge barrier to essentially do research in this domain. But with our special partnership with Siemens, for example, they do allow us to sort of get into the guts of the machine while working within the regulatory, being compliant with the regulatory approvals, to essentially have us access to this raw data, which sort of spawns kind of research problems that people have not necessarily been able to solve traditionally, right? And other examples includes our recent partnership, or not so recent anymore, I guess a few years ago, with Facebook, where essentially we leveraged our access to this raw data from MR to use deep learning models to speed up the image acquisition process. So instead of a patient spending 40 minutes within an MR machine, with our deep learning based algorithms, they can now spend maybe 10, 15 minutes and get the same amount of information, or at least the same amount of data to less amount of data to create a similar quality image, right? And this research itself has basically resulted in an explosion of a subfield within the MR and AI community, where people are now racing towards building models, AI models that can expedite images, the image reconstruction process. Then the fourth thing is the data. I mean, again, like as I said, it's a School of Medicine is quite a giant institution, and to just to give you a little bit of a scale as far as the data is concerned, we have a lot of data, right? Like, I mean, on an average, in the School of Medicine, about 35 million procedures of various kinds are done or administered on an annual basis. Like 35 million is a pretty big number as far as healthcare data is concerned, right? And just to break up this number, we have about 11 million lab tests on an annual basis. We have about 3 million biopsies on an annual basis, about 3 million imaging studies that are acquired on an annual basis, and about 1 million ECGs, for example. So it's a huge number. And it's not just the number per se, it's also sort of the diversity of the data that is important, especially if you're building machine learning models that have to be generalized across different communities and different socioeconomic people with socioeconomic status and different demographies. So the good thing, as I said, is the School of Medicine is not just limited to Manhattan, but spans sort of multiple areas around the NYC metropolitan area and also in Long Island. And as a result, the kind of patient population that we see on an annual basis is quite diverse. Right? And then the fifth thing is the science, right? Like one thing that I've learned as far as both during my startup and I guess mostly during my startup, and as a result that made me actually join the School of Medicine and Courant at NYU 4 years ago, is that most people have this perception, especially in the AI community, that we don't really like, all we need is access to medical data. And once we have access to medical data, we will figure out how to solve the problem, or whatever the problem is, right? Like, we will take a deep learning model, which could be potentially off the shelf or whatever, and then press a button on this data, and then something will come out, and that'll probably result in a solution to a problem. That sort of assumption could not be further from the actual truth, right? In order to really do successfully do interdisciplinary science and research, one has to have a close collaboration with domain experts, right? And without that collaboration with domain experts, machine learning cannot and will not make any difference, right? And that is something that sort of this partnership between CDS and School of Medicine tries to solve. The School of Medicine has some excellent people who are experts in their specific domains, whether it is physicists who know the ins and outs of an MR machine, or whether they are the geneticists who've been working on this for essentially multiple decades, or whether it is histopathologist, or whether it is neuroscientists and stuff like that. So what School of Medicine provides is access to that domain expertise for folks like you all, who are more on the computational side of things, to sort of have a nice collaboration or a nice marriage that can actually result in a successful research. And yeah, and that, I mean, I could not sort of emphasize enough as to how important this access to domain expertise is if you really want to have a successful career in this interdisciplinary field, and School of Medicine has that. And then lastly, I would say the impact, right? Like, as I said, like we have lots and lots of problems that we focus on in diverse areas, but the underlying theme in most of the problems that we focus on are essentially how impactful they are in the real clinical setting or in the real world, right? Some of the examples of the short-term impact that we've had, basically, which came out of the collaboration between the CDS, Courant, and the School of Medicine, is basically our work during COVID, when folks from CDS worked closely with the clinician in the School of Medicine to devise and deploy solutions to triage patient during COVID, essentially to get a sense of, given a patient with a specific set of symptoms and their potential medical history, how likely are they to have sort of their symptoms deteriorate in the next week or 2 weeks or 3 weeks time, and based on that they could make an assessment whether how much medical resources, which were scarce around that time, to provide this to this patient, so as to sort of improve the overall care of the community. And as far as long-term impact is concerned, so that was an example of a short-term impact, right? And as far as long-term impact is concerned, like we pay special attention to working on like really high impact problems that can truly transform healthcare and AI. Like one prime example is everywhere scanners in the Department of Radiology, where we are hard at work now on developing medical imaging scanners of the future, which can actually transform how we actually acquire images, right? Like the current standard of care is, if you need to get an MR done, or if you need to get a CT done, or any medical imaging done, you need to pick up your phone, get an appointment with the imaging center, and wait for the appointment for a few weeks down the line. And then once you get an appointment, which will highly likely be at an odd hour sometime during the week, you have to take an off, you have to go to an imaging center. Essentially half of your day or your full day is lost, right? So the kind of things or the kind of problems we are solving, or in addition to like straight up medical imaging analysis, is basically how can we change this paradigm of, instead of bringing the patient to an imaging device, how about we bring the imaging device closer to the patient, right? I mean, maybe have cheaper accessible devices that are placed in CVS's of the world or the Walmarts of the world, where you can go in and get a quick scan done, and the scan would say, okay, probably something is wrong. You really need to go get a full scan or a full appointment done, right? The other example of such long-term impact, which again most people are not necessarily working on, are things like what I call discovering the unknown unknowns, right? Like right now, like as I just mentioned in my data slide, we are acquiring data at an unprecedented scale, right? I mean, every time you go, you have a little bit of a chest pain, either you get a chest X-ray or an EKG, or sorry, an ECG and stuff like that, right? And up until now, for the most part, I would say research in AI and ECG, for example, is done primarily to take an ECG as input and predict all the clinical conditions that a human currently a human clinician is currently able to diagnose, like whether you're suffering from an AFib, or if there's anything else wrong, like as far as your specific heart condition is concerned. But if you think about it, like ECG is a really rich data source, right? It consists of 12 channels, and it's basically a continuous waveform. Now, what exactly is stored in that data right now, nobody knows, right? I mean, especially a human does not know, because that's that's not how clinicians look at those waveforms, which are not necessarily human interpretable for the most part, other than for a few conditions. So the question is, what is it what is it that we are throwing on the table with this rich data that we've already acquired? Can we extract additional signal about things like, I mean, there's been research by one of the CDS faculty member themselves about how reliable an ECG signal is to predict whether you'll have diabetes in the future, for example, something that a cardiologist would never even think about. So questions like that, like essentially those fundamental questions that that can truly transform healthcare using AI is what we are very much interested in as in School of Medicine. But yeah, don't just take my word for it. I mean, you'll hear from a couple of faculty right after me to give you a little bit more detail about the kind of problems they have been working on, and happy to answer any questions.
Thank you, Samit. So there a number of questions related to how to tailor an application for the medical school track. Do students who are applying have to have a medical or medical related background? What are medical school track faculty looking for?
Yeah, so answer to the question of whether you need to have a medical background, the answer is no. You do not. So, like as I said, the medical school faculty is quite like they have huge expertise on the clinical side, and essentially what they are looking for people who are very computationally inclined but passionate about making a difference on the clinical side as well, right? Like of course, like if you're working in areas like single cell biology and uh, 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 computational genetics, etc., the expectation is that yes, you need to have some understanding of biology, but again, like that's something that Aravinda can speak more about it, who'll be speaking right after me, who's by the way a world leader in the space. But the general expectation is that you should be strong on the computational side and passionate towards on the making an impact on the clinical side. That's the expectation from a medical school faculty. As far as tailoring the application is concerned, again, I would strongly encourage students to explore sort of the CDS website and also the School of Medicine website and people's faculty pages and see the kind of work they are doing and whether that interests them. And then, of course, like they should mention the names of those people in their application so that those applications can be looked at by them.
Thank you, Samit. Thank you for joining us today. I am gonna share my screen to introduce the next speaker. Okay, so we're moving on to lightning talks by medical school track faculty and researchers. So first up, we have Aravinda Chakravarti. I hope I pronounced that correct. And Aravinda, I'm gonna stop share so you can share your screen. Oh, and you're muted. Oh, still muted.
Go here.
Oh, yes, I hear you now.
And you can, I need to do slides, let's see. Okay, can you see my slides?
I see, yes, an overview of all the slides, yes.
Okay, let me get to the back, okay. So, okay, good morning or afternoon, wherever you are. I'm Aravinda Chakravarti, a faculty member here in the School of Medicine. And I'm going to use some very specific examples to amplify on some of the points that Sumit already has made. So one of the words that I mean, the last point that Sumit was trying to make as to whether one really needs to be very medically qualified or knowledgeable to do it is increasingly, just like in our, real lives, I think there's a whole cadre of people growing up, trainees who are becoming increasingly bilingual. And here on the scientific side, bilingual means that there's lots of people with interests, people such as you out there, who come from a background in computation, in computer science, statistics, mathematics, modeling, and are learning the guts of another science. You heard Guy talk in the beginning as to how his journey went. So this is the same on the medical school tract side as well. For example, many years ago, but my original training was in mathematics and in theoretical statistics. And I sort of went down this path, and I did get training in experimental biology, and I think it's enabled me to solve a range of problems that are far more interesting than I could have in only one domain. I'm speaking about myself. So I'll tell you a little bit of, I think, one of the most informational molecules that we know, that we all inherit, and it's DNA, it's our genome. And I think it's a fascinating scientific problem of how the sequence is read, how cells are made, trillions of cells, and how they carry out a genetic program that is all in this 3 gigabases of DNA. And that's our genome. And each of us inherits 2 genomes, one from each of our parents. But then genomes get chemically modified in various ways during a lifetime. And that's what an epigenome means. That means the sequence is not altered per se, but rather it is altered chemically at that point in time. So that alteration is not inherited, but everything we are exposed to, these epigenomes are also a very important part of the biology and disease each of us have. And a lot of this epigenetic also appears to be genetically controlled. And so my lab has been trying to develop this area to try and understand what their roles in human disease could be. So for a long period of time, genetics and genomics has focused on what are so-called monogenic disorders like thalassemias or sickle cell anemia that's common in many parts of the world, or cystic fibrosis that's common in other parts of the world, and we've all worked on it. But increasingly, what we would want to do is study diseases that are called complex. And they're complex because it's not from a single factor, it's from many factors, and these factors interact. By the way, I'm not going to read this. This is more for me to know how to carry on this conversation with you. And so there are many, many genes, and our role, or the scientific problem, is to find these genes, find what is variable or variant or mutated in these genes, and how is it that those genes cause very specific phenotypes. In this case, this is a birth defect where a child is born without a nervous system in their gut. Each of us have 3 kinds of nervous system, the one in our brain, which is the central nervous system. We have the spinal cord, which is not completely independent of the CNS, but still it has some autonomic action. And then the one in our gut, which is the enteric nervous system, which is almost independent, but does have all connections to the CNS. And if you don't have a nervous system, it's okay while development occurs in the womb, but with the first meal, as soon as a child is born, there is no peristalsis in the gut, and it leads to very severe disease with the death unless people intervenes. And so, again, without details, my lab and other labs has spent a lot of time in trying to figure out the original hard genetic way on what are the components that are involved in this disease and how they interact. And in this case, we have a theoretical model, and the importance of any model, a computational model, or in this case, a cellular model, is when you understand some parts of it, you can understand the missing parts essentially by some kind of analogy. So here, by studying this kind of disorders or a number of disorders, here's a model. And the advantage of a model is that we can now try to identify its component for any disease from the human genome sequence of patients. And essentially, our programs are to teach you on how to do this and to improve on the methods that already exist. So here, for example, is a cartoon of a gene. There's a small bit of the genome. This arrow shows some sequence that is used to produce a particular message. And these boxes represent other sequences that are the non-coding part that regulate how much of A is made, where it's made, when it's made. Making a gene or making a product is actually a very expensive business. It requires a lot of energy. And so these controlling sequences have turned out to be very important, and one of the major roles that we've had in defining them. So this produces some amount of message or even the protein. And the genes that are relevant to a disease, there are many of them, and they produce different levels. So the red marks here point to sequence differences between you and I, for example. And for this gene, I make more than the mean. Here, I make much less than the mean. Here, I make the modal or mean amount. And all of these signals get integrated by what we call a regulatory network. That is, their outputs, one, this is a usual kind of engineering systems diagram, where the input of one changes the output of some gene. And all of this, of the thousands, tens of thousands of genes that are made in any cell, gets integrated for the disease I showed you. By the hard way, we figured out what that integration, sort of measure is. And what it does is alter cell behavior. In that case, it's lack of cell proliferation or death, shown here by the smaller number, which is what leads to the absence. These perturbations don't have to be sequenced. They could be epigenetic. And these could arise from chemicals. It could arise from many other sort of exposures that we have. And so our big attempt, one example of what we do, is to try and use the sequence to learn where the genes are, which we've known from the Human Genome Project, but where these regulators are, or regulating sequences are. So most of you are probably quite aware of how many machine learning models work. Here we take some random sequences, which is the negative training set. And some of these enhancers or regulatory sequences we already know. And in this case, it's actually very appropriate that we can use SVM kind of training to identify the specific sequences. Here done by essentially indexing all 10 mers, 11 mers. This can be elaborated in many ways to find not only the sequence that regulates that gene, the sequence can have gaps and so on and so forth. So we've been doing this for a while in collaboration with many people in my labs and other labs. And the advantage of a model is, if I know what the sequence does, which is the one on the top, if I alter that sequence by a mutation on a variant, then my model can predict what happens to that gene. And that's precisely what we do. Here are other experiments to show that this prediction works. And we, a few years ago, did the first such maps of using whatever this kind of appropriate data is to identify these cis regulatory elements, or called CREs. There are hundreds of thousands of them, and we identified them. We identified at least a suite of proteins that likely interact with these genes and the genes they regulate. All of this is fine. Models are fine, but they have to work, in this case, on a gene by gene by gene basis. And what we show here, without going into all of the details, here's a sodium channel. It's very important for regulating heart rhythm. In fact, mutations in this gene lead to very early congenital arrhythmias. And here we show is, at least so far as expression of the gene is concerned, in the heart, our predicted expression and our observed expression. This is observed from material that we've gotten from, from autopsy material, is actually pretty good. And of course, our job or our interest is to make this kind of prediction even better. So this has given a number of investigators, including us, the idea that we can make reference data sets, say, for example, surgical tissue that we have access to, or from autopsy material that connects the specific sequence to the activity of genes. And what this allows us to do is to take your sequence and my sequence and predict the activity of a gene that otherwise we would not know. So these are known sort of regression and learning methods. We've now used various other kinds of deep learning. And what we can do is not only for one tissue, we can do it for many, many, if not all, human tissues. And what this allows us to do is try and ask, what are the tissue contributions, not just the genomic contributions, to something as common as, say, blood pressure? And these are recently published work, and I'll give you just one flavor of it. We know that when you look at just genes, some of the genes are ubiquitous. They're found in many, many sort of tissues. Others are tissue specific. They could be heart specific, adrenal specific, kidney specific. Each of these genes, as I told you, genes are controlled by many of these CREs, some of which are ubiquitous, whereas others are tissue specific. And then when you look at the sequence of any one of these CREs, they can be interrupted by very many variants. Some of these variants are found elsewhere and have effects that are broad, whereas others are tissue specific. And here it shows that for blood pressure, what are the contributions of genes, the sequences that regulate the genes, and the specific variants that alter the regulation of those genes? And what you find is the specificity at the level of genes is about 36% of the variance in blood pressure. When you get to CREs, it's about half. When you get to the specific variants, it's even much greater. It's about 3/4. So it just tells you that the human genome as a machine, if it's to regulate blood pressure, what it does is through different mechanisms of adding specificity. It's not like this gene by itself will do it, but specific regulators of those genes have an added level of specificity, whereas sequence variants that all of us have add to a third layer of specificity. This just shows that even if these tissues were all equal in their contributions to blood pressure, by the time you take variants such as this, you find that some kind of tissues have a much greater contribution to blood pressure. And so much of our research program is to try and identify these effects and find the specific machinery that regulate, in this case, blood pressure, or better still, abnormalities in blood pressure control, which is hypertension. We also work on EKGs and ECG parameters, as well as those that lead to arrhythmias. And here, for example, is some recent work that we've done in data that has been publicly available. There's a lot of human disease genomic data publicly available. And what this does is a very simple PCA plot of looking at that entire epigenome in this case. And all we are doing is each circle here is a different subject. Some are fetal, and the best we know from the metadata are healthy. Others are healthy or hypertensive adults. And what you see is the kind of new biological features we are learning. First, this is a very simple analysis, as you can tell, is the first principal component, which is the major one, divides all fetal samples from all adult samples. So human fetuses or young, even, in this case, right after birth, these tissues have quite different functions than what one does, in an adult. And even in an adult, across the entire genome, we can see these kind of epigenetic differences between those who are healthy and those who have hypertension. And if these kinds of data turn up and on a disease-by-disease basis show these kinds of signals, then the genome actually gives us a way in order to find the specific genes, the regulators, and the variants that alter a normal developmental process to lead to disease. And so the final implication of that is we don't have to treat the symptoms of the disease as we do now, because we don't know the basic causes. but we can deal with the basic causes themselves. And much of what we do is actually computational. Much of what we do is actually building models to understand how the genome works. So I'll stop there and take any questions if you have them.
Thank you, Aravinda. I guess we're a little bit short on time, but a general question for you is whether you are accepting candidates for this admission cycle for 2025, and do you have a preference for interested prospective students to be contacting you directly via email, and what you're looking for?
Correct. So I have been and I am taking students for the next couple of years based on the grants that we have and active grants we have. About half my lab are increasingly purely computational people. And so if anybody is interested, they can reach out to me directly. As somebody said, I think Guy said very importantly in the beginning, the more specific you are, we can have a much more specific conversation.
Great. Thank you very much.
Thank you.
Let me share my screen to introduce the next speaker. So next we have Nicolas Coudray, Senior Bioinformatics Programmer at the Applied Bioinformatics Laboratories, and who is under Professor Aristotelis Tsirigos. Sure Nicolas can pronounce that better than me. Nicolas, I'm going to stop share screen for you.
Okay, thank you. Thank Tina. So as Tina said, I'm a senior scientist in Tsirigos lab. You see my slide? So Aris is, yes, he has his own lab with a lot of projects, which I will tell you, but he's also the director of the Applied Bioinformatics core facilities and co-director of the Division of Precision Medicine. And the kind of research that we're doing is really around one mission, which is to improve the patient care by harnessing emerging technologies, and especially like the multimodal data, AI, but a bunch of others. And the three goals are really centered around the understanding of disease. So they are how they work, mostly cancer, but not only cancer, but a big amount of our research is around cancer. The diagnosis part, improving the diagnostic, making it more precise and more specific to each patient. And the treatment. So again, each cancer, as you may know, is kind of different for each patient. So how to make a precision medicine, so treatment that's really adapted to each patient. And to do that, so we use a bunch of different techniques, which you see around. So there's like image analysis, there's some epigenomic, genomic information, transcriptomics, bioinformatics. So it's really a large field and really interesting, and a lot of opportunities to interact and learn from all of those fields. So to show you a bit better what you were doing exactly, I'm going to just show you two examples of two projects which were completed in the past year or past 2 years by PhD students in collaborations. So the first one was done by Adal, and it's been published this year in Nature Communication. And the second one, which is done by Jiming, we just graduated and did this actually like last week. So I'm doing his PhD, so he made this what's called the origami approach, which I will tell you about, and which was published in Nature Biotechnology in 2023. So for the first approach, so those of you which were not familiar with pathology, so usually when you have a cancer, the tumor can be resected, it's going to be sliced, it's going to be put on a slice, which is called a wall slide image, and it's going to be submitted to the pathologist who will look at it and basically just make a diagnosis. So it will say whether there's a cancer, what kind of cancer it is, and there's a lot of information in those images. So here's just a tile, but you can imagine that those images that the pathologist has to look at are huge. They are like 1,000 times bigger than this. And you have inside, you have a lot of different cells. So you have the tumor cells, but also the dead cells, the cells from the immune cells we're going to attack. So, and from all of those information, the pathologist is going to try to make the best diagnosis that he can, but it's very time consuming. So that's where the use of AI basically has come in the past, has really increased in the past 6 or 7 years to really assist in this task. And as you can, because these images are big, it's also like not only time consuming, but also prone to human errors when you have like so many to do in a short time. And in the past few years, there's been a lot of algorithms which are published, which for those of you who know, were called like supervised learning. And in supervised learning, what you need to do is basically train your algorithm for a specific task. And the task, so for this task, you need labels. So for example, if you want to train to recognize a tumor, you would need someone to annotate the tumor. Usually it will be a pathologist or specialist. And the annotation part is also very tedious, very time consuming, and cost a lot of money to get. In the past 2 or 3 years, there's been this new type of algorithm which were used, which are called self-supervised. And this is the one that we've been doing with this collaboration with Adal. It's basically developing a platform that can visually learn the pattern in the medical images. And it's based on what's called the Barlow twin method and approach. And basically, it's one image, the same distorted version of the image, which is given as an input to the network. And the network will basically learn that the image and the distorted image is the same. So what will happen as the training goes on, it will have in this latent space, basically each images will be kind of, we can say coded, will have a barcode associated. And each images which basically look similar or contain the same type of information will have a barcode which is very similar. So then we can use these dimension reduction approaches to represent each tile or each image on a UMAP. And the ID is like each dot is a tile. And basically based on their position, if they're close to each other, it means that they share the same barcode. It means that they share the same phenotypes. And here, why is it interesting? Because basically now the AI has built a kind of a landscape, which is represented by this UMAP, where it has learned on its own without annotation to recognize the different morphologies. So for example, each tile which will be located on the top left of this UMAP will be what's called a solid tumor. Those which are on the bottom left will be what's called a lipidic tumor kind of morphologies. And on the right side, you have all the benign type of morphologies like the lymphocytes, some necrosis, and just some normal tissues that you find. In this case, it was done on lung cancer. So here we had some just normal lung looking like tissues. So why do we want this kind of a phenotype representation, and what can we do? So you can then map them back into the whole slide image. On the left side, you have an example of one subset of an image, and then on the right-hand side is just the different clusters and morphological phenotypes that were identified by the AI. So basically, it will give you a simplified interpretation of the very complex tissue. And then built on top of that, you can then use regression model or interpretation to see what you can predict. So with this, you can predict what's the tumor, what's the subtype of the tumor, but also what we're interested in is kind of predict and understand the survival of the patients and the risk that the patient will have a poor survival after resection, or the risk that the survival of the patient after resection will be good, and we will likely survive a long time. And this is a survival curve, for example, for one example. And in the x-axis, you have the different phenotypes automatically identified by the AI. And here you have the curve, which will basically tell you if it goes up to, it will tell you that basically it's predicting a recurrence of the tumor. And if it goes down, it means that basically it thinks that the prognosis for this given patient is pretty good. But the advantage of those approaches compared to supervised approaches is that it will not only make a prediction, but it will tell you why it makes the prediction. And here, for example, you see that when the curve is flat, it means that all these morphologies basically do not really influence much the decision that he has made. And you see that here, when it goes up, it tells you which morphologies has been used to make this decision. And it says that, oh, I think that the prediction of recurrence is high for this patient because I see this kind of a pattern in the slide. And as this was mentioned by the other talks before, this is always like studies which are done, of course, with pathologists and validated by the pathologists. This is always a very collaborative process because, yeah, you don't do much by just sitting behind a computer. You need really to interact and exchange with pathologists, try to understand those kind of things and what are the needs, and validate what you do. So it's also very interesting to be able to also have this very collaborative setting. So that's for the first project. The second project I wanted to tell you is the one from Jiming. And he built this deep learning model, which is called Theorigami. And the goal was to learn gene regulation and 3D genomic interactions. So what is it? So the 3D chromatin organization, usually, it determines what genes are going to be expressed. And why is it important? It's because gene expression analysis can then be used to classify disease like leukemia, but also predict what the outcome of the leukemia can be. And on the left-hand side, you have some kind of example. So usually HiC is the name of the technique, which is based on the next genome sequencing approach, which is very costly approach. It's been used historically to basically describe this 3D organization. So here you can imagine by basically the chromosomes are organized in what you have. It's like a compartment, and in each compartment, then here you also have what's called TAD, so the topology associated domains. And on the left-hand side, these kind of triangles is just a description of how the DNA is organized. So in the x-axis, you will have the sequence. And then here, basically, when it's red, it means that those parts of the DNA are very interacting. So it basically describe the 3D organization of your genome. And what Jiming did, like, okay, it's like this NGS-based approach is really expensive. Can we, using AI, predict this 3D organization by using other type of information? And the 3 types of information that is used is like DNA sequence, what's called ATA sequence, and CTCF. And using these 3 inputs, then is able to show that he can predict as well the 3D organization of the genome. And 2 examples of the impact of what it means to be able to have Theorigami predict the genome. So on the left-hand side, you have an example of disease with the CUT-LL1 T-cell leukemia type, which this particular leukemia harbor a chromosomal what's called translocation. So this is just an illustration of what this is. Basically, it's just swapping one part of a gene into the chromosome 9, which goes into chromosome 7. And on here, it's basically how a typical output is for the analysis of 3D organization. And at the bottom, you can see how it has been predicted by his AI algorithm. You can see that it's really close. And it's a really nice representation of the 3D information that is really characteristic of such a disease. So basically, it shows here that it's basically able to predict those TAD. So basically, the topologically associated domain was called the neostripe, also, which are really hotspots for DNA damage, and which are located near the breakpoint of this specific leukemia. So it can basically characterize the type of leukemia. And on the right-hand side, the second advantage of being able to use AI, that you can do it also in silico and make some kind of discovery how new regulatory elements will basically influence the 3D organization of your genome. And in this example, for example, cause a loss of insulation. And what's the consequences when you do that? So it gives you an insight into how gene regulation is altered in cancer, but also it can eventually help you to discover how new therapeutic targets can potentially impact it and have influence, and it will help with the development of those targets. So those are the kind of work that we're doing. So I say it's mostly, cancer therapy, trying to understand how it works, trying to make better diagnoses and better therapies. Those projects are usually very collaborative. And as I said, our Tsirigos has his own lab, but it's also part of the applied bioinformatics core. It's part of the precision medicine department. So we're surrounded by a lot of staff scientists, data research scientists, other PhD and postdoc doing diverse projects, more or less related to each other. It's also the kind of project where you do need to work with a pathologist because they have the knowledge and the know-how of cancer. People who prepare the samples and generate the data is also those people have also the knowledge on what's the best way to use this data, what's the best way to process them, and so on. We've had collaboration with other universities. For example, the first project was done with University of Glasgow in UK, and much more. So yeah, and here I put Tsirigos with the head of the lab email. So in case you have more questions later and want to ask him something more specific, yeah. And also if you have questions now, feel free to let me know.
Thank you, Nicolas. I think you actually answered the most important question, was how to contact your lab and if your lab was accepting students. So thank you for the email address on the screen. And as mentioned in the beginning of this webinar, the webinar is being recorded and will be shared. It'll be posted on the CDS website, so you'll have access, and we will try to collect all the slides and share those too, but you will have access to the recording. Nicolas, there's a question in the Q&A. I'm not sure if it's a question you can answer. It's what are the probability of starting an entrepreneurial journey after having a PhD from medical track?
I mean, AI is we're working a lot of AI, and it's really a fast moving track. And I know people from NYU. I mean, in this case, those I know is well established. I mean, who have startup, and basically what we're doing a lot of development. But then after development, yeah, there's also all those parts which we have. Okay, now that we have a project and we basically have this ID. For example, a few years ago, we had this model that's able to identify. We've shown that we've been able to identify mutations just looking at the images of whole slide images. And the implication is that if you're able to do that, then you save a lot of money and time, because doing the genome sequencing on the tissue is really super cost expensive and not everyone can access to it. So now there's, for example, on this project, a goal to move it to a startup and say, okay, now that we have the idea and we know this is possible, like let's move it forward and make it work, and let's build it. So I think it's definitely possible with the good, you can have the good ideas, the good team, and the good way to move forward, and that's all you need.
Thank you, Nicolas. And I'm not sure if this was in your slide, but someone's asking for the title of the Nature Communication paper for Project One. If you wanted to answer that question in the Q&A, or is it already in your?
Let's see. Yeah, I can add it in the Q&A. Yeah.
Okay, great. It's one of the last questions in the Q&A views. Scroll down.
It's called HPC, histopathology morphological phenotype. But I can write it because it's yeah.
Thank you, Nicolas. And let me share my slides again.
Oops, let me unshare.
Okay. Sorry, I didn't introduce myself earlier. I'm Tina Lam. I'm the Assistant Director of Graduate Programs. I'm just going to quickly go over some admissions and application reminders, and hopefully this will answer a lot of the frequently asked questions that's been appearing in the chat and in the Q&A module, and that we've received via email. So admission requirements, CDS welcomes applications from candidates with relevant undergraduate or graduate degrees. We don't require that you have a graduate degree. GSAS does require that you have received or will receive your undergraduate degree, a US equivalent from an institution of recognized standing before enrollment. And I included the link there, what the academic transcript requirements are. If you have more questions about your eligibility on this front, the Graduate School of Arts and Sciences admissions office will be the best office to answer those questions. Applicants should have coursework or equivalent experience in calculus, probability, statistics, and programming. We don't specify a specific level for those, but as long as you've had relevant coursework either as an undergraduate or have done certificate programs in these areas, they will be accepted. And there's an area in the online application for you to outline your experience and coursework. This is a full-time program. Admitted students are offered fellowships that cover tuition fees, and health insurance. The fellowship includes also a competitive stipend, and the fellowship packages are for 5 years for fall and spring semesters. Application requirements. The TOEFL or IELTS is required for all applicants who are speakers. Am I muted? Okay. So the TOEFL or IELTS is required for all applicants who are not native English speakers or who do not have a bachelor's or master's degree from an institution where the language of instruction is English. Again, master's degree is not required, but for those who did complete a master's degree, if it was in English, it can replace the TOEFL or IELTS requirement. College transcripts, 3 letters of recommendation, preferably on the recommender's letterhead. The current institution is fine. It doesn't have to, if they've moved on from the institution from when you've interacted with them, they can put their current institution's letterhead. Statement of academic purpose. GRE scores are optional. They're not required, nor are they recommended. It does not affect you positive or negatively if you submit them, but if you feel like it's an important part of your application, would like us to review it, then you can include it in the application. There is no minimum GPA requirement, and more details about the admissions requirements can be found on our website, which is linked on this slide here. The fall 2025 online application is now open. You can access it through the Graduate School Application Resource Center, which is linked here. GSAS and CDS offers a very limited application fee waiver program. You can find details about these programs within the online application. So when you create an application, you select the data science PhD program, you will find a section where there's more information on how to apply to either program. The application deadline is Thursday, December 5th by 5 p.m. Eastern Time. We don't accept late applications and there is no priority deadline. We are unable to do pre-application reviews. We get a lot of inquiries about applicants' backgrounds, including their CVs. We cannot state whether you're a competitive applicant or not, as long as you fulfill the requirements and submit the required application components. We'll review your application to see if you're a good fit. All submitted applications will be reviewed after the December 5th deadline. Decisions will be available in February. The PhD program is only available for fall admissions. We do not admit for spring. So the online application right now is for starting the program in fall 2025. Typically that's around September of 2025. So this is the thank you for joining us today screen, which includes relevant links. If you have unanswered questions, you can email us at cds-admissions, but I'm going to be quickly going over the Q&A module just to see if there's any questions. Quickly answer.